In this video here, we're going to take a look at Leibniz's theorem and nth derivatives. So Leibniz's theorem is a powerful tool in calculus that allows us to generalize the product rule for differentiation and also find the nth derivative of the product of two functions. So if y equals uv here, where u and v are functions of x, then in that case, dy by dx is equal to u times dv by dx plus v times du by dx. And you should hopefully recognize this here, right? Or I would certainly hope that you recognize this. This here is the product rule. Now, if we apply the product rule again here, then what we obtain is the second derivative of y, which is equal to u times the second derivative of v plus dv by dx times du by dx. And again, we get the same here. So dv by dx times du by dx. And then finally here, the second derivative of u. And then clearly we can simplify this here, right? So the second derivative of y is equal to u times the second derivative of v plus two lots of dv by dx times du by dx. And then finally here, v times the second derivative of u. And if we repeatedly apply the product rule here, we obtain the following. So for the third derivative of y here, that's equal to u times the third derivative of v plus 3 lots of du by dx times the second derivative of v plus 3 lots of dv by dx times the second derivative of u plus v lots of the third derivative of u here. And just one more time for good measure then. So for the fourth derivative of y here, that's equal to u times the fourth derivative of v plus 4 lots of du by dx times the third derivative of v plus 6 lots of the second derivative of u times the second derivative of v plus 4 lots of dv by dx times the third derivative of u, and then finally here v times the fourth derivative of u. Now, you might be able to spot the pattern that's happening here, and what I'd recommend then is just looking at the coefficients here. So 4, 6, 4, this would be 1 and 1 here. Same again for the third derivative here, so 1, 3, 3, and 1. And then same again here, 1, 2, 1. And hopefully you can spot the pattern here. So let's just generalize what is basically happening here, and which is Leibniz's theorem. So let's formally introduce here Leibniz's theorem. So the nth derivative of a product of two functions follows a pattern that is summarized by Leibniz's theorem. So Leibniz's theorem gives a general formula for the nth derivative of the product of two functions. So if y equals uv, where u and v are functions of x, then in that case, the nth derivative of y here is equal to the following. And this looks a little bit intimidating, right? But it's not too bad. And I think the best way to demonstrate this is to run through a practice question, which we'll do shortly. But what I want you to notice here then is the fact that we use n choose k here. This is our binomial coefficients, right? Which in other words, just follows Pascal's triangle. So that's what I was referencing on the previous page when I was mentioning the coefficients, right? These are the binomial coefficients, okay? So this here then is Leibniz's theorem, and it's particularly useful because, as we've already mentioned, it allows us to find the nth derivative of the product of two functions, okay? So that concludes our introduction here to Leibniz's theorem and nth derivatives. We've kind of shown the pattern and how this generalizes then to the nth derivative. So I think the best way to actually demonstrate this is to just run through one practice question. So let's get started then on our practice question here for Leibniz's theorem and nth derivatives. So let's just have a go then at this one practice question here. So as we can see then for this question here, all we want to do is use Leibniz's theorem to calculate the third derivative of y for y equals e to the x cosine x. So to begin with here then, we're going to let u equal e to the x. So u is equal to e to the x, and v here is equal to cosine x. Okay. So for the next step here, what I want then is the first, second, and third derivative of u with respect to x. And the same is true here for v, right? So I want the first, second, and third derivative of v, again, with respect to x here. So starting off then, we have du by dx here. So du by dx is simply e to the x. And this is true for each further derivative. So in that case, the nth derivative here is simply e to the x. But what I want to do here is write down each derivative just so you can see the working in full. So for the second derivative here, this is dx squared here. Again, we get e to the x. And then for the third derivative here, And then finally for the third derivative here, that's dx cubed. Again, no prizes here, right? It's just simply e to the x. Okay. So let's do the same here then for v. We have dv by dx here, which is minus sine x here, right? I had to think about that for a moment. So minus sine x there. So now for the second derivative here, this is equal to minus cosine x. And then finally for the third derivative here, this is equal to sine x. Okay. So what I'm going to do now is actually state Leibniz's theorem for this derivative here. So in that case then, third derivative here of y by Leibniz's theorem is given as follows. So it's the summation here. It's the summation from k equals 0 to 3, because we're looking for the third derivative, right? So from k equals 0 to 3, we then have 3 choose k. So 3 choose k here. And then we times this by our product of derivatives here. So in that case then, we get the following. All over dx to the power of k. And then we times this by the following here. So this is to the power of 3 minus k here. The v all over then dx here to the power of 3 minus k. So what might help here as well is if we just state the binomial coefficients here. So we're going to have 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. Got 3 choose 0. That would give us 1 here. 3 choose 1, which is 3. We have 3 choose 2, which again is 3 here. And then finally, we have 3 choose 3 here, which gives us 1. So now we have everything that we need here to find the third derivative of y equals e to the x cosine x. If we continue here then, well, starting off we have 3 choose 0. So 3 choose 0 is 1. So what I get here then is 1 times by u times by the third derivative of v here. So in that case then we get u times by the third derivative of v. Like so. Now for the next term here then, we get 3 choose 1. So that's 3. So I get 3 lots of the first derivative of u here. So this one will now increase to the first derivative, and this one will decrease to the second derivative. So I get 3 lots of du by dx. So 3 lots of du by dx here, times by the second derivative of v here. Okay. We now have 3 choose 2. So again, that's 3 here. So we get 3 lots. And again, this one will increase here to the second derivative, and this one will decrease here to the first derivative. So we get 3 lots of the second derivative of u. Like so. And then we times this here by the first derivative of v. So dv by dx here. And we should have just about enough room here to finish this first line of working. So now this one will increase to the third derivative of u, and this one will decrease to just v. Okay, and we have 3 choose 3, so it's just 1 here as our coefficient. So in that case then, what we get here is v times by the third derivative of u, like so. Okay, so let's use all of these substitutions here then. Okay, so or what these expressions are equal to, I should say. So u times by the third derivative of v here. So that's u, which is e to the x here, times by sine x. So I get e to the x sine x, like so. We then get 3 times du by dx. So that's 3e to the x, so plus 3e to the x here, times by the second derivative of v, so that's minus cosine x. So this would change from a plus to a minus here. So cosine x, and change the plus to a minus. So plus becomes a minus like so. So So now for the third term here, we have 3 lots of the second derivative of u times dv by dx. That's 3 lots of e to the x here. 3 lots of e to the x here. Then we times that by dv by dx, which again is negative. So this will change from a plus to a minus, but dv by dx is sine x. So we'll write down the sine x here and then change the plus to a minus. Like so. And then finally here we have v times the third derivative of u. So the third derivative of u here is just e to the x, times that by v, which is cosine x. So what I get here then is plus e to the x cosine x. Okay? So if we simplify this here then, what we can see is for the third derivative here. So for the third derivative here then, what we have is minus 2e, because I've got e to the x sine x here, but we've also got minus 3e to the x sine x here. So that simplifies to give us minus 2e to the x sine x here, like so. And doing the same here then with this cosine x term, so minus 3e to the x cosine x plus e to the x cosine x. That simplifies to give us minus 2e to the x cosine x. Okay. And at this point here, right, you could just leave your solution as follows. If we just kind of factor out here and make it look a little bit neater, what we get here then is minus 2e to the x bracket sine x plus cos x. Okay, just looks a little bit neater, right? So sine x plus cos x there. And there we have it. That gives us the third derivative there. And that gives us the solution then to this one practice question here for this video. And that actually brings the end then of this video here on Leibniz's theorem and nth derivatives.